Welcome to our deep dive into sets. Looks like you've given us some excerpts from a math textbook. So we're going to, I guess, unravel this whole fundamental concept of sets together.
Yeah.
But we're not going to do it like a lecture or anything like that. We'll hit the key ideas.
Of course.
But also, uncover those kind of surprising details that make even, seasoned mathematicians kind of raise an eyebrow or two.
Yeah, you've hit the nail on the head. Sets are so foundational to math, it's easy to overlook their depth.
Yeah.
But trust me, even in those basic definitions, there are hidden layers just waiting to be explored.
So to kick things off, how about we tackle the most basic question? What is a set, really?
Right.
I know there's a formal definition and all that, but is there a way to think about them that, doesn't make my brain melt?
Absolutely. Imagine a basket.
Yeah.
You can fill it with apples, oranges, maybe even a stray sock if you're feeling chaotic. That basket, in its simplest form, represents the idea of a set.
Okay. I can picture that.
Right.
So how does a basket, like full of random stuff, translate to a formal mathematical concept?
Well, in math, a set is officially defined as a collection of distinct objects.
Okay.
And we call these objects elements. Think of it like a club with a very specific membership. Each object has to be unique. No duplicates allowed.
So if I put like two identical apples in my set basket,
Right.
Is that breaking the rules?
It does. Each element has to be distinct. So even though they're both apples, they have to be considered separate entities. But the order we put them in doesn't matter at all.
Okay.
It's all about who's in the club, not where they're standing.
Got it. So what kind of things can be members of this mathematical club? Is
Right.
it just numbers, or can things get a bit wilder?
Oh, things can definitely get wild. Numbers are the usual suspects: whole numbers, fractions, decimals, the whole gang. But you can also have sets with symbols, equations, geometric shapes, even points in space.
Wow.
And, get this, you can even have sets containing other sets.
Hold on. Sets within sets. That's like having a basket inside another basket, which itself is inside another basket.
Yeah.
Things could get out of hand pretty quickly.
It's a bit like those Russian nesting dolls. It might seem strange at first, but this idea is actually crucial to how sets work.
Okay.
And why they're so powerful in math.
All right. So we've got our baskets.
Yeah.
And we know they can hold all sorts of, fascinating mathematical objects. But how do mathematicians actually talk about sets?
Right.
Do they just list out everything inside?
Well, listing everything out works for smaller sets, and we call that roster notation.
Okay.
It's simple. You just write out all the elements within curly brackets, separated by commas. For example, if your set contains the first three letters of the alphabet, you'd write open curly bracket A, comma, B, comma, C, close curly bracket.
Okay, so far so good.
Right.
But what if our set has, say, 100 elements? Writing all that out would get pretty tedious.
You're absolutely right. That's where things get a bit more interesting. We have a little shorthand for that too.
Okay, let's hear it. My hand is getting tired just thinking about writing out 100 elements.
Let's say your set is all the even numbers between 2 and 100.
Okay.
Instead of listing them all, you'd write open curly bracket 2, 4, 6, comma, ... comma, 100, close curly bracket.
Yeah.
Those 3 dots, called an ellipsis, basically tell everyone, hey, this pattern continues until you hit 100.
That's a lifesaver. But I can imagine there are sets out there where even that trick wouldn't cut it. What if the set is never ending?
You've stumbled upon the concept of infinite sets. Sets with an unlimited number of elements, and yes, those definitely exist. Take the set of all even numbers, it keeps going forever.
So how do we wrangle those infinite beasts with our notation?
We use the same ellipsis trick, but we just don't put an endpoint. For example, the set of all even numbers would be 2, 4, 6, ... with those 3 dots trailing off into infinity.
All right, that makes sense. But I'm already sensing a potential problem here. What if two people describe the same set in different ways?
That's a great point. And it brings us to another crucial aspect of set notation: clarity. It's like learning a new language. You have to be precise to avoid any misunderstandings.
Yeah, I'm starting to realize that there's a lot more to sets than meets the eye.
Right.
I'm guessing mathematicians have come up with even more ways to define them.
You bet. There's another way to describe sets called set builder notation.
Okay.
And it's especially handy when dealing with more complex or infinite sets. Instead of listing everything out, you define the set by stating a rule or condition that its elements must satisfy.
So it's like setting the criteria for membership in our mathematical club.
Exactly. Think of it like a secret password that only members of the set know. Let's say you want to describe the set of all even numbers. Instead of listing them out, you could say, the set of all integers n such that n is divisible by 2.
Wow, that's much more efficient than an infinite list. It's like a code that unlocks the set's secret identity.
Exactly. And that's the beauty of set builder notation. It lets us define even the most intricate sets with a concise and unambiguous formula.
Okay, so now we got a good handle on what sets are.
Yeah.
And the different ways to define them. But I have a feeling we're just getting started, right?
You're right. We've only scratched the surface.
Yeah.
There are many more fascinating concepts to uncover, like the idea of sets within sets, which we touched upon earlier. And trust me, things get even more interesting when we start exploring relationships between sets.
Well, you've definitely piqued my curiosity. I'm ready to dive even deeper into the world of sets. What's next on our agenda?
Let's explore the idea of subsets, sets within sets, and how they can illuminate the intricate connections between different mathematical objects.
Lead the way. I'm all ears. Okay, subsets, sets within sets. It's like we're going down a mathematical rabbit hole here.
Right.
But before we get too lost, can you give me like a real world example of how this works? I'm a bit visual.
Sure.
So something I can actually picture would help.
Of course. Let's say we have a set that contains all the books in the world, a pretty massive set, right? And within that set, we have a smaller set that contains only science fiction books. Every science fiction book is also a book.
Right.
So we can say that the set of science fiction books is a subset of the set of all books.
Okay, so it's like having a giant library and then a special section just for science fiction. I'm starting to see how this nesting idea works.
Exactly. And we use a special symbol. This kind of looks like a sideways U with an underline underneath.
Okay.
To show this a subset relationship, we'd write science fiction books, then that symbol, all books. Now, there's also the concept of a proper subset, which is a bit more specific.
Okay, what's the distinction here? Does it have something to do with like those hardcover versus paperback debates?
Not quite. A proper subset means the subset is smaller than the original set, not equal to it. So while every science fiction book is a book, not every book is science fiction. That means the set of science fiction books is a proper subset of the set of all books. We use a slightly different symbol for a proper subset. It's that same sideways U, but without the underline. Okay.
So it's like saying that a Chihuahua is a dog, but not all dogs are Chihuahuas.
Exactly.
Okay, makes sense. But you mentioned earlier that even the empty set, that basket with nothing in it, is considered a subset of every set.
Right.
That still feels a bit strange to me.
It is counterintuitive. But remember, for a set to be a subset of another set, every element in the smaller set has to also be in the larger set. Since the empty set has no elements, it automatically meets that criteria.
So it's like saying an empty box can fit inside any other box, regardless of its size or content.
Exactly.
Okay, I can see the logic there, but it still makes my brain do a little flip.
Yeah.
Are there any tools that can help visualize this?
Absolutely. Euler and Venn diagrams are great ways to represent set relationships. They use circles or other shapes to represent sets, and the way those shapes overlap or are contained within each other shows how the sets relate.
Oh, right. Yeah. I remember those from school. The visuals definitely help make those abstract concepts a bit more concrete. Speaking of abstract concepts, you mentioned earlier that there are some sets that are considered VIPs in the math world.
Right.
What makes them so special? Are we talking about sets of like rare butterflies or something?
Not butterflies, but something just as fascinating. These are sets of numbers so fundamental they have their own special names and symbols. They're like the foundation upon which so much of mathematics is built. We'll start with a set you use every day, the natural numbers, represented by the letter n. This set includes all the non-negative whole numbers. 0, 1, 2, 3, and so on.
The counting numbers.
Exactly.
It's amazing how something so basic can be so important in math.
They're the building blocks of arithmetic. Now, if we add all the negative whole numbers to the mix, we get the integers denoted by the letter z. So we have ... -3, -2, -1, 0, 1, 2, 3, ... and so on in both directions.
So integers are like the expanded universe of natural numbers. They cover the entire number line, not just the positive side.
A great analogy. Now let's venture into the realm of fractions. The rational numbers, represented by the letter Q, include all numbers that can be expressed as a fraction, where the numerator and denominator are both integers.
So that includes all those familiar fractions like 1/2, 3/4, -7/4, and so on.
Precisely. And don't forget that all whole numbers are also rational numbers, since they can be written as a fraction with a denominator of 1. For example, 5 is the same as 5/1.
Okay, so the rational numbers are like a big tent that includes both fractions and whole numbers.
Now let's expand our horizons even further and step into the realm of the real numbers, denoted by the letter R. This set includes all the rational numbers plus all the irrational numbers.
Irrational numbers, that sounds a bit mysterious. What makes them different from the rationals?
Irrational numbers can't be expressed as a simple fraction of integers. Think of numbers like pi, that infamous ratio of a circle's circumference to its diameter.
Right.
Or the square root of 2. They have decimal representations that go on forever without repeating.
So they're kind of like the rebels of the number world. They refuse to be neatly contained within a fraction.
A perfect way to put it. And finally, we arrive at the most inclusive set of all, the complex numbers, represented by the letter C. This set builds upon the real numbers by adding in the imaginary unit, denoted by the letter I.
Imaginary numbers. I remember those from school, but they always felt a bit like mathematical magic.
They do have a certain mystique about them. The imaginary unit I is defined as the square root of -1, a concept that initially seems impossible. Complex numbers combine real numbers with multiples of I, opening up a whole new dimension in mathematics.
So complex numbers are like the ultimate mathematical expansion pack. We've gone from counting numbers to numbers that can't even be written as fractions to numbers that includes the square root of -1.
And the fascinating thing is that each of these sets neatly nests within the next, like a set of those Russian nesting dolls. Natural numbers are a subset of integers. Integers are a subset of rational numbers. Rational numbers are a subset of real numbers. And real numbers are a subset of complex numbers.
Wow. It's quite a hierarchy.
Right.
But I have to ask, why should we care about all of this? How do these special sets of numbers impact our lives outside of, a math textbook?
Right.
Do I need to brush up on my complex numbers to, balance my checkbook?
That's a great question. While you might not be using set notation or complex numbers in your daily life, understanding these different sets of numbers is crucial for many fields.
Okay.
For example, engineers use complex numbers to model electrical circuits, and statisticians use real numbers to analyze data.
So even though we might not be consciously thinking about sets and number systems, they're, working behind the scenes in so many areas of our lives.
Exactly. And that's the beauty of mathematics. It's a language that describes and underpins so much of the world around us, even if we don't always see it directly.
This has been a fascinating journey through the world of sets. We've covered a lot of ground, from basic definitions and notations to the surprisingly deep concept of subsets and the hierarchy of special number sets. But I'm sure there's still more to uncover, right?
You're right. We've just scratched the surface of what makes set theory so fascinating and powerful. There's a whole universe of set operations, relationships, and paradoxes that mathematicians are still exploring today.
Well, you've definitely sparked my curiosity to learn more. I can't wait to delve deeper into this world and see what other mathematical treasures I can uncover. When we started this deep dive, I thought sets were going to be pretty straightforward.
Right.
Like just, a bunch of stuff grouped together.
Yeah.
But we've uncovered so much more than that. Subsets, special number sets, those mind-bending infinite sets. There's a real depth to this concept I hadn't appreciated before.
That's what makes sets so fascinating.
Yeah.
They seem simple on the surface,
Right.
but they open up this whole world of mathematical exploration. And the best part is we've only just begun to explore their potential.
Before we wrap things up, I'm curious. You mentioned earlier that sets are used in various fields beyond pure mathematics. Can you give me some specific examples of how sets are applied in the real world?
Absolutely. Sets are like a secret weapon in many fields. For example, in computer science, sets are used in database design, algorithm development, and even in programming languages themselves.
Oh.
Think about searching for something online.
Okay.
You're essentially defining a set of criteria.
Right.
And the search engine finds the web pages that match those criteria.
So every time I type a search query into Google, I'm unknowingly using set theory.
You are.
That's pretty cool.
It is.
Yeah.
And in statistics, sets are used to analyze data and draw conclusions.
Okay.
For example, if you're conducting a survey, you might divide your respondents into different sets based on their age, their gender, or location.
Okay.
This allows you to analyze the data within each set.
Right.
And then compare the results between the sets.
I see. It's all about organizing information and finding patterns. So
Yeah.
sets are not just for mathematicians, scribbling equations on a chalkboard.
Right.
They're a tool that helps us make sense of the world around us.
Precisely. And the applications go even further. In finance, sets are used to model investment portfolios and manage risk. In linguistics, they're used to study the structure of languages. Even in music, sets are used to understand chord progressions and scales.
Wow. It seems like sets are everywhere. Once you start looking for them, it's like we've unlocked a hidden code that reveals the underlying structure of so many things.
You've got it. Sets are a fundamental concept that transcends individual disciplines.
Yeah.
They provide a common language for understanding relationships, patterns, and structures in a wide range of fields.
Well, you've definitely given me a newfound appreciation for the power and versatility of sets.
Good.
I'm going to start looking at the world through a different lens now,
Yeah.
seeing those hidden set structures everywhere.
That's the beauty of learning something new.
Right.
It opens up new ways of seeing and understanding the world.
Mm-hmm.
And who knows, maybe you'll even discover some new applications for sets in your own life.
I'm ready for the challenge. Thanks for taking me on this incredible deep dive into the world of sets.
Of course.
It's been an eye-opening experience.
It's been my pleasure. Remember, even though our deep dive has come to an end,
Right.
your exploration of sets is just beginning. Keep asking questions, keep exploring, and most importantly, keep that sense of curiosity alive. There's a whole universe of mathematical wonders waiting to be discovered.